right, so let's do a couple of more examples involving exponential growth models, population growth models. Example 5 here, suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 days after the fourth day. Who's counting these flies? Approximately how many flies were in the original population, which is a total silly question, simply because if you really wanted to know that, maybe you had a box of these things when you started this experiment and the box said quantity. There's like 30 flies or something like that. You would have already known. Anyway, that's the problem that we're given. Let's see if we can solve this particular thing. All right, and coming back over here, don't look at the graph. This is spoilers. Example 5. So for example 5, we've got a couple of pieces of information. Oh, are you looking at that graph? I see you looking at that graph. First of all, we're talking about the law of exponential growth. That is a key to understand that we are going to use y is equal to c e to the kt, which of course came from the model dy dt is equal to k times t, right? It arose from that. I don't want to have to solve it. I'm just going to understand that that's how it solves. All right, so we know that we have the equation. It's still in pink. Change it. Y is equal to c e to the kt. All right, so far so good. And then we have a couple of conditions here. There were 100 flies after the second day of the experiment. So we've got 2, 100 as one of the points. And then we also have 300 flies after the fourth day of the experiment. 4, just looked at it, 300, and already forgot. And what we want to know is how many flies were there on initially. So basically we're trying to solve for that C value that's there. All right, so let's give it a try. And first we're going to plug in, let's pick some nice little colors here. We're going to plug in our 2 and 100 into our equation. So we have 100 for our y value is equal to c times e to the k times 2, but I'm going to write that 2k. All right, and then how about purple for the second one, just because that's going to be pretty. And then for that one, we're going to plug in 300 for the y is equal to c e to the 4k this time. All right, and for the rest of this problem, we're solving a system of equations. So we want to solve that system of equations with substitution. And it may have been a minute substitution. I think I spelled it correctly. It may have been a minute since you've solved such a system of equations by substitution, like exponential ones anyway. And the suggestion here is to take one of these equations and solve it for c, and then you can plug that into the other one. That's exactly what I'm going to do, because essentially we've got two variables. We've got the c variable, and we also have the k variable. So we're going to solve one of the equations, and I'm going to suggest this first one, and solve that thing for c. So doing that, we end up with 100 over e to the 2k is equal to c. Now I'm going to take that and substitute it back into the second equation in order to find out what the k value is. So this goes right in here. Now we're going to do some algebra and simplify this down. So we have 300 is equal to, in parentheses, 100 over e to the 2k times e to the 4k. All right, and I'm going to rearrange some stuff here. I'm going to just write the 100 by itself, and this e to the 2k and this e to the 4k I'm going to combine up. One is on the top and one of them is on the bottom. Just to make it obvious, I'll rewrite it over e to the 2k. And now these have the same exact base, so you can subtract the exponents and simplify your equation as 300 is equal to 100 e to the, subtract those exponents, just get 2k. Right, and now we're solving this thing for k, so I'm going to divide by 100. Why am I trying to change colors? I don't know. I got 3 is equal to e to the 2k. You know what we're about to do. I'm going to take the natural log of both sides. Okay, so I've got the natural log of 3 is equal to 2k. Divide by 2, and we can see that k is equal to 1/2 of the natural log the natural log of 3. You could, if you wanted to, rewrite that as the natural log of the square root of 3. Doesn't really matter. All right, so we have our k value. Now, the question was asking how many people, and by people I mean flies, were in the initial population, which is C. And we already have an equation for that. So all we have to do is take our k value that we just found here and plug it into that equation, and we can figure out how many flies were in the initial population. So our C is equal to 100 over e to the 2 times our new exponent here. Just zoomed in a little bit because why not? Natural log, 1/2 natural log of 3. Let me zoom back out. Okay, good. All right, simplifying. The 2 and the 1/2, those guys are going to cancel. And I've got e to the natural log of 3, and then more canceling because of some inverse properties. I get 100 over 3, which is about 33. 33 and a third, sure, but should not having a third unless you got some mean kid laying around a third of a fly. So we're going to say that there were approximately 33 flies in the original, that's not how you spell that word, original population. Ta-da! 33 flies-ish. Now let's look back at that graph that I was trying to hide from you. And you can see from that graph, it has a little speech bubble. That equation is talking to us, and it has a little 33 right up front, and that 33, of course, is supposed to be our initial population. All right, one more of these, and that's going to polish off this objective. Example 6. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. Okay. If the sales follow an exponential pattern of decline, what will they be after another 2 months? And you can see in the margin, here's an example of this, a very famous example. I think there's actually a documentary on like how this affected this E.T. game back in the day, how it affected Atari and specifically the whole entire video game industry. It goes crash. Anyway, let's take a look. Look, there's the equation right there. We're already done. Okay, end of lesson. We've got example 6, the ET question. Not really. I just put that picture there because I thought it was funny. We've got exponential decline, pattern, exponential decline, which implies that we are using the same exponential equation, y equals c e to the kt power. All right, and then we have a couple of points that we're going to use. You see, like, after you make this conclusion, exponential pattern of decline, your calculus is done. It's all algebra from here on out. So we've got a couple of points that we're going to put on here. So after 4 months, the advertising, After 4 months of advertising, man, I'm having a hard time reading that. Anyway, we've got 100 units drops down to 80,000 units. So in other words, we're going to assume we're starting out at 0, 100,000, right? And you can even see that in our equation here that you're not supposed to be looking at. And then 4 months later, so this is going to be a time t equals 4, we're down to 80,000 units per month. Okay, so those are our points that we're going to plug in there. The first one, extraordinarily easy. We just know that this means that this is our initial value. It's the same thing as our c. Just plug it in. So we have the equation y is equal to 100,000 e to the kt. And now we have another variable to solve for. That's our k. And we're going to use our second point to solve for that one right there. Plug that guy into our equation, and we're going to go ahead and inadvertently zoom in a little bit. Okay, that's good. Plug that in there, and then solve that thing for our k value. So 80,000 goes over here is equal to 100,000 over here, e to the k times 4. So I'll just write that as 4k. All right, and do yourself a little bit of canceling. Like these zeros cancel, as do these ones, those ones, and then we're left with dividing by 10. Get 8 over 10 is equal to e to the 4k. Doesn't even look like a k. Still doesn't. There we go. Maybe it's a little bit better. All right, and maybe reduce our fraction to 4/5 e to the 4k. Oh my gosh, I wonder what we're supposed to do next. How about take the log of both sides? And we get the natural log of 4/5 is equal to 4k, which means that k is equal to 1/4 of the natural log of 4/5. And yeah, sure, you can use some algebra and simplify that if you want to, plug it into the calculator, get an approximate answer. But if you do that, just make sure that you use as many decimals as possible before you round to get your final answer. Okay, so I'm going to rewrite my exponential decay equation as y is equal to 100,000 e to this new exponent, which is 1/4 natural log of 4/5, all of that times t. All right, so far, and now it's asking us, what will they be? As in, what will the sales be after another 2 months? After another 2 months, our data went to 4 months, so this means that we're talking about t equals 6 months. So we're going to plug 6 into our equation and see what happens. Y of 6 is equal to 100,000 e to the 1/4 natural log 4/5 times 6. All right, again, pretty much calculator at this point. Let's just plug the whole thing in there. 100,000. Is there enough zeros there? I think I maybe need one more. E to the, and then our exponent was this 1/4, I'll just put 0.25, natural log of 4/5, 4 divided by 5. Okay, I'm going to arrow out of that and then also multiply that thing by 6. And let's approximate that one, and we get 71,554. You can ignore the rest of the little decimal points, okay, because we're talking about numbers of units, which is approximately equal to 71,554-ish units per month. Box your answer and call it a day. All right, so that concludes this lesson. This particular objective was applying differential equations to exponential growth and decay, and we saw that it gave rows to the equation y is equal to c times e to the kt.